In the last video, we saw the definition of a topological space being either reducible or irreducible, or connected or disconnected. And these definitions are pretty short, they're easy to state. But then when you're given a concrete topological space, it can be hard to check because it requires you to basically check all unions of two closed subsets, whether they can cover the space without being the entire space, for example. And for the concrete spaces like X being affine varieties, we would like some tools to check this. And the go-to tool in algebraic geometry when there's really some hard stuff to be done is to go to commutative algebra. So we would like some criterion on X or on the ideal cutting out X to tell us whether X is reducible, irreducible, and so on. And this is kind of the main result of this video, that when you have an affine variety, let's say it's non-empty inside AN, then the following are equivalent. One is that X is irreducible. Two, in terms of the ring of the coordinate ring of X, or the ring of polynomial functions on X, this is a domain. And three, that the ideal of X inside this ambient coordinate ring is a prime ideal. So we have characterized this topological notion purely in terms of commutative algebra terms. So for the proof, one equivalence is very straightforward. Namely, we know that A of X is just K of X1 up to Xn modulo this ideal. And so the equivalence between these two just stems from the general commutative algebra fact that if you have R a ring, like this polynomial ring, and I an ideal, like the ideal of X, then the quotient R modulo I is a domain, an integral domain, if and only if I is a prime ideal. And that's not a deep lemma. You basically just plug in the definition of being a prime ideal, you plug in the definition of being a domain, and then it's kind of a two-line argument. So that these two are equivalent, that's not a surprise, and this could have been a commutative algebra lecture. And now we're going to see what does it have to do with X being irreducible. And one of the directions is pretty straightforward. So I want to show I implies II. So we do this by proof by contradiction. So assume A of X, this coordinate ring, was not an integral domain. And then this not being an integral domain means that we can find two elements in there which are non-zero, but their product is zero by definition. This is just the data that we have given, not 2i. And now what we need to come up with is a union x1 union x2 giving us all of x. Well, we already have two functions around. What we can do is we can take x1 to be the vanishing locus of the first function, x2 the vanishing locus of the second function. Then, since these are not the zero function, I claim that then xi is a strict subset here. The reason just not being a zero function means that there's at least one point where you're not zero. And this is a point of X where the fi doesn't vanish, and so it's not in the vanishing locus. And so therefore, this is really a strict inclusion of set. So basically, we just followed the path of least resistance, and now we have these two closed subsets, and they happen to already be proper subsets of X. And then we can hope maybe this is just enough if we take the union of those. So this is a union of vanishing sets. Already last time, we reminded ourselves, this is the same thing as the vanishing set of the product of these ideals. And then this just gives you the ideal generated by the product, so F1, F2. But now we look back at our assumptions and we saw F1 times F2 is 0. So we have the vanishing locus of 0. Well, 0 vanishes everywhere. And so this is all of X. And so indeed, we have obtained our X as a union of two proper closed subsets. This part wasn't so hard. the converse direction, there you have to have kind of one idea. So assume that X is reducible and these two subsets are closed, then we need to show that A is not a domain. And well, if we have this strict inclusion, this means now we go to this kind of level of ideals, of relative vanishing ideals. If you have this inequality, then I claim that this relative Nullstellensatz tells you that also the ideals of these two sets are not the same. So we left this relative Nullstellensatz as an exercise, but what it really does is it tells you there's a bijective correspondence between subvarieties of X, and then by this taking the ideal, you land in radical ideals of A of X. And this is a bijective relationship. And so in particular, if these two are not equal, then the ideals are also not equal. And so, well, the ideal of X in the coordinate ring of X, these are all the functions which vanish at every point of X. Well, this is just a zero function. And so what this just tells you is that the vanishing ideal of the Xi is not just zero. Well, if it's not just zero, what we can do is we can choose non-zero functions fi in this ideal. And now we have gotten ourselves again two functions, two elements in AX. We want to show it's not an integral domain. So what we can do, we can try to hope that the product of these two functions is zero. And this is exactly the next claim. And indeed, well, what we see is F1 was in this ideal of X1, which means F1 on X1 is zero. F2 on X2 is similarly zero. And so if you take the product, well, the product of two functions is zero exactly on the union of the vanishing loci of these functions. In particular, this product here is zero on the union X1, union X2. But, well, now we look back again at our assumptions, and these were exactly the sets that cover X. So this function is zero on all of X. But then, I mean, restricting to the entire domain just doesn't do anything. So zero is equal to F1 times F2. And on the other hand, we have chosen the Fi to be non-zero. And so indeed, we have demonstrated AX is not a domain. So in this proof, we mostly followed the path of least resistance. We just plugged in the definitions. And the one thing where you had to have one input was that the fact that these are really proper subsets means that their ideal is not the zero ideal. Okay. And so we have this characterization of when an affine variety X is irreducible. And we can, as a corollary, we can kind of upgrade this relative Nullstellensatz to say that if you have some ambient affine variety Y, then you get a bijection between the non-empty irreducible affine subvarieties in Y and the prime ideals in A of Y. So the original relative Nullstellensatz would have told you that if you have the just any affine subvariety in Y here, this correspondence would be a bijection to the radical ideals here. So we're already starting to basically give the proof. So this is the usual relative Nullstellensatz correspondence. And then if you restrict to being non-empty irreducible here, well, then the theorem tells you that conversely, here you are prime ideal in this ring of functions. And so the proof basically just follows directly from the previous result. Okay, so that was the kind of theoretical prediction, and now we can look at some examples and apply this. So First of all, if you have an affine variety which happens to just be a finite set, we know finite sets are always affine varieties, like this, then the claim is this is irreducible if and only if it is connected, if and only if it contains at most one point. And indeed, otherwise, if it contains at least 2 points, then you can cover it with 2 proper non-empty subsets by taking the first subset to be the first point, the second subset to be the rest of the points. These are both closed sets still. They're both not the entire set, but they cover this. And not only this, but also you see that they're disjoint by definition. And so this proves not only is Y reducible, but in fact, it's also disconnected if R is at least 2. So this actually is the sum for this finite set. We didn't need any commutative algebra, but then what we can do is we can look back and see, well, if Y just has a single point, then the ring of functions, we have seen the single point as vanishing ideal, a maximal ideal of the form xi minus the coordinates of this point. And then the quotient is indeed just the base field k, and this is of course an integral domain. So that was a kind of baby example, I would say. Then more interestingly, one thing which we claimed is that we hope that A1 is an irreducible space. And in fact, now we can see that the whole affine space AN is irreducible. And thus, as we have seen, irreducible always implies connected. And for this, we just observe that the ring of polynomial functions on AN is just a full polynomial ring. And this is an integral domain, simply because K is an integral domain. And then if you iteratively take the polynomial ring in one additional variable, this remains an integral domain. And so this result from commutative algebra immediately tells you something about the topology of AN. And then finally, something of our running example. So we had seen this example of X, which was the vanishing locus of this polynomial into variables, and we could decompose it like this. This was the real picture of this. And this decomposition told us already that X is a reducible space. And now what we can observe is that this can no longer be further decomposed. This x1 is not the union of x10 and x11. So indeed, this x1 and x2 are irreducible. And we can check this. In this case, it's very easy to calculate the coordinate rings, because A of x1, this is just the quotient of the polynomial ring modulo this ideal here. And then if you look at this quotient, you see this ideal allows you to take the variable y and replace it by x squared. And so you can eliminate the variable y, and so actually this is isomorphic just to k of x, which is a domain. And similarly for x2, there the ideal is just x, and you can then just eliminate the variable x and get k of y. This is also a domain. And then by the criterion, this being a domain means that x1 is that x1 and x2 are irreducible. And similarly, we had this example of kind of two parallel vertical lines. And similarly, you can check this ideal allows you to eliminate the x variable, and the same here. So on our to-do list for this running example, we did show that the xi and yi are themselves irreducible. What is still to show is that x is connected, and there we're going to see kind of a fully general recipe how you can check this if you know something about these irreducible sets decomposing your variety. And this is also kind of a segue to the next video. So we did decompose in this example X as a finite union of irreducible spaces, which cannot be decomposed further. And we proceed now by studying a general class of such topological spaces which admit decompositions of this form.